Okay, in 2.1, we talked about what an inequality is, what problems involving inequalities look like, how to represent them with graphs, with interval notation, what it looks like to see them in words. Now we're going to talk about how do we actually solve a problem that involves an inequality. And we're going to connect this right back to what we learned in Unit 1 when we were solving equations. We were solving equations, we were using the addition property of equality, multiplication, division, all of those properties of equality, and some of them are going to tie to properties of inequalities. So just like with Unit 1 when we were solving equations, to solve an inequality, our ultimate goal is to isolate the variable, and we can do that by using these following properties and inverse operations in general. So all of these properties below hold if we're talking about greater than, less than, greater than or equal to, less than or equal to. And in fact, these properties are going to look really similar to what we talked about in Unit 1. The addition property says we are allowed to add as long as we add the same number on both sides of the inequality. We will still have a true statement. So you can see that over here in the algebra column mathematically. If A is less than B, then we could add some C to both sides, and we still have a statement that's true. I think it's easier to see this with numbers. It is true that 9 is less than 12. So if I added 5 on both sides, I would then have 14 and 17. It is still true that 14 is less than 17. Similarly with subtraction, we can subtract as long as we subtract the same number on both sides of the inequality. So if I subtracted C, this should be a B. If I subtracted C on both sides, I would still have something that is true. Let's look at that with numbers. If I subtracted 5 on both sides, 9 minus 5 is 4, 12 minus 5 is 7. This is still true. So we started with something that was true, we subtracted something on both sides, and we still have a true statement. Addition and subtraction hold. Multiplication and division hold in a similar way, except there's one key word here that I want to draw your attention to, and that word is positive. We can multiply or divide on both sides of an inequality by the same number as long as that number is positive. And the reason we can't do this with negative numbers is that if you think about the number line, when we multiply or divide by a negative sign, that actually changes the direction that we're looking at on the number line. So it's fine to multiply both sides by 5. If I changed one of these to negative numbers, that's not going to be true anymore. So 9 is less than 12. If I multiply both sides by 5, 45 is still less than 60. If we multiplied by negative 5, that would make it say that negative 45 is less than negative 60, and that's actually not true. Negative 60 is much, much smaller than negative 45. So this property only holds true when we are multiplying or dividing by a positive number. So that should raise the question, well, how do we deal with negative numbers? Do any of these properties hold true, or what do we do when we have to multiply or divide both sides by a negative number? Because that's bound to happen. And that's what you're going to see down here in red. If we are multiplying or dividing by a negative number, what you do to make this statement hold true is you flip the inequality. Whichever direction it was facing, you're going to flip it so it's facing the opposite direction, because we're really bouncing to the other side of the number line, and flipping the inequality is the only way to keep it true when we're multiplying or dividing by a negative number. So we can add, subtract, multiply, and divide on both sides, and it stays true. The only thing we need to remember is that if we're multiplying or dividing by a negative number, we need to flip the direction of the inequality sign. Now that we have identified these properties, let's look at some examples where we're actually going to use them to solve an inequality. So number 1, for all 3 of these examples, we're going to be solving each inequality and graphing our solution. We're also going to make sure when we solve, we write the answer as an inequality and using interval notation. So the first problem, m minus 5, is greater than or equal to 8. So our ultimate goal is to isolate m. What is preventing m from being by itself? Right now, it's that minus 5. So what we can do is we can add 5 to both sides. That's going to give us that m is greater than or equal to 13. I'm going to go ahead and graph that. So the key number on the number line is 13. I'm going to just put it in the middle. I'm going to go up a couple lines and put 14. I'm going to go down a couple lines and put 12. It's going to be a closed circle because there is an or equal to, and it's going to point to the right because it says m is greater than or equal to 13. Interval notation, since that circle is filled in, I'm going to have a square bracket. The lowest that this graph goes is 13, and it's going up forever, so from 13 up to infinity. Number 2, 7 times m is greater than or equal to negative 42. How do I get m by itself? I need to get rid of 7. What are 7 and m doing? They're multiplying. So to undo that multiplication, I'm going to divide. When do we flip the inequality? I want you to stop and think about that for just a minute. Should we flip it here? So I know that I'm going to have m. I know I'm going to have negative 42 divided by 7. Do we flip the inequality? We do not. We did not divide by a negative number. 7 is a positive number, so our inequality is not going to change. I'm still going to have m is greater than or equal to negative 6. So I'm going to put negative 6 on my number line. I'm going to add a couple more numbers. Closed circle at negative 6, and it's greater than or equal to, so it's pointing to the right. Number 3, interval notation. So the lowest this ever goes is negative 6, and that is a closed circle, so square brackets, and it's going up to infinity, going up to the right forever. On number 3, I don't like that my variable is on the right. So the very first thing I'm going to do is I'm going to rewrite this problem, and I'm going to switch everything around. It makes me feel much more comfortable, and it makes me know I'm going to graph correctly as long as my variable is on the the left side of the problem. So I want W to be by itself. Right now, W is being divided by 3. To undo that division, I'm going to multiply both sides by 3. So over here, those 3's are going to divide out. I'm going to have W. Over here, negative 2 times 3 is negative 6. What did I multiply both sides by? Positive 3, so I am not going to flip my sign. So I'm going to make sure negative 6 is on my number line. That's going to be an open circle because there's no or equal to, and it's going to be pointing to the left. W is less than or equal to negative 6. For the next 4 examples, we are going to solve. We are not going to graph. So if you feel ready, go ahead and pause this video and try and work through some of these sample problems. All right, number 4. I want to get all of my x's on the right. So I'm going to start by adding 7x to both sides. 4x plus 7x is 11x minus 2 less than or equal to 9. I'm going to add 2 on both sides. That's going to give me 11x is less than or equal to 11. And then I'm going to divide both sides by 11, so x is less than or equal to 1. If I write that in interval notation, x is less than or equal to, so it's going down forever. The highest it will ever be is 1, and it's or equal to, so I need a square bracket. Number 5, I want to get negative 3y to be alone on the left side, so I'm going to subtract 8. So negative 3y is greater than or equal to positive 21. To get rid of the negative 3, I'm going to divide. So now, ding, 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 we are dividing by a negative number, so we have to flip our inequality sign. The direction it's facing, I'm going to flip it to face the other direction because right now we are dividing by negative 3. That's going to give me that y is less than or equal to negative 7. Interval notation, it's going down forever. Square bracket because it is or equal to. Number 6, to get x plus 5 by itself, I need to undo this dividing by 2. To undo dividing by negative 2, I'm going to multiply both sides by negative 2. I'm multiplying by negative 2, so that's setting off an alarm in my head that I'm going to need to flip my inequality. So on the left, I'm going to have x plus 5. On the right, 3 times negative 2 is negative 6. To solve for x, I'm going to subtract 5 on both sides. That's going to give me that x is less than negative 11. Then I'm going to write that in interval notation. It's going down forever, so negative infinity. It's going up to negative 11. It is not or equal to, so I'm going to have parentheses here as well. Now, I know some of you are looking at number 7 and your brain is going crazy because you see all of these scary fractions. I want you to pause the video and see if you can multiply by a common denominator to make this problem a little bit less scary. So I'm going to go ahead and get rid of all of the fractions by multiplying everything by 6. So if I multiply 6 by 2/3, 6 times 2 is 12. 12 divided by 3 is 4. So this whole first term is just going to become 4f. If I multiply 6 by 1/2, half of 6 is 3. I'm not multiplying by a negative number, so I'm not going to change the sign. 6 times 1 is 6. Divided by 3 is 2, so 6 times 1/3 is 2. Remember, when you multiply fractions, you multiply across the top and across the bottom and simplify. So that one step got rid of all these scary fractions. Now we can subtract 3 on both sides. Subtracting 3 is going to give me 4f is less than -1. Now to get rid of the 4, we can divide both sides by 4. So that's going to give me that my final answer is that f is less than -1/4. In interval notation, that means I'm going down to -infinity. The highest value is 1/4. And it's not included, so I'm going to use parentheses. Notice all of these problems had negative infinity instead of positive infinity because in the end, they were all less than. If you ended up with a problem that was greater than, your number would be on the left-hand side and your infinity would be on the right-hand side. So I have actually run out of space for my word problem on the bottom. I'm going to do it up here on the top where number 3 was. Sammy has a gift card. She has already used $14 of the total value, which was $30. Write, solve, and graph an inequality to show how much more she can spend. So the very first thing I want to do is define my variable. So I'm going to let X be the amount that Sammy, can spend. I know that no matter what, she can't spend, so less than or equal to, she can't spend more than $30. $30 is how much is on the gift card. She has already spent $14. So the amount that she has plus the $14 that she's already spent has to be less than or equal to 30. If I solve this, this means that she can spend $16 or less. So we have written our inequality, we have solved it, now we're going to graph it. And I'm just going to use this number line. I'm going to put 16 in the middle. I'm going to put a closed circle on 16. Something that I want you to notice is that this graph would actually stop at 0 because she can't spend a negative amount of money. That's something that we're going to talk about when we get to the next section, 2.3, which involves compound inequalities. For right now, I just want you to think about that. She can't spend a negative amount of money, so this has to stop at 0. The very last thing we're going to talk about are special cases. So if you remember in Unit 1, sometimes we got weird answers like no real solution and all real numbers. So I'm hoping you're kind of thinking, does that happen with inequalities? What does it look like? And the answer is yes, it does happen with inequalities. It is possible that in the process of solving, all of your variables go away and you're left with something like 4 is less than or equal to 40 or 3 is greater than 5. You're going to ask yourself the same exact question that you asked yourself last unit. Is what's left true or false? If it's true, like it is here, this is true. 4 is less than or equal to 40. If what's left is true, that means no matter what you plug in, you're going to get a true statement, which means that all real numbers is the solution. Every possible number you could plug in would work. If it is false, like 3 is definitely not greater than 5, that would be false. That means your answer is going to be no real solution. So this is going to happen anytime you're solving and the variable completely goes away. The answer will either be all real numbers or no real solution, just like with Unit 1. You just have to think a little bit harder about what's left. Is it true or false when we have inequalities? So let's look at 2 cases just like this. On number 8, if I subtract 2x on both sides, I'm left with -7 is less than or equal to 5. So all my variables go away, so I'm asking myself, is this true or false? Is -7 less than or equal to 5? Well, it's not equal to, but is it less than? Is -7 less than 5? Yes, this is true. What that means is every single number on the number line would work. So when I graph that, I'm just going to graph the entire number line. Similarly, on number 9, if I distribute 6y minus 4 is greater than or equal to 6y plus 21. If I combine like terms here, I'm going to get negative 8. 6y minus 8 greater than or equal to 6y plus 21. If I subtract 6y on both sides, I'm going to get negative 8 is greater than or equal to positive 21. Well, negative 8 doesn't equal 21, so that's not true. Negative 8, is it greater than 21? No. Since neither thing is true, the answer to this is false. And that means you aren't going to graph anything on your number line because nothing that exists on that number line could possibly work. So the answer here would be no real solution. The answer here would be all real numbers, which means if you think about this graph, negative infinity to positive infinity, everything possible works. So to recap this lesson, we talked about using the properties that we established in Unit 1, but now with inequalities to solve. We can add, subtract, multiply, and divide on both sides as long as we do the same thing to both sides. We will still have a true statement. The one exception to that is if we are multiplying or dividing with a negative number, then we have to flip our inequality sign. We learned what it looks like to graph those solutions, just ties right back to 2.1, and then we analyzed the special cases that could exist with all real numbers and no real solution. So please take the time as needed if you need to go back and review this video. Otherwise, we will be reviewing problems just like this in class. Thank you.